Everyone, this is Josh. I'm gonna be going over the cosmological constant problem. I'll be following Weinberg's 1989 paper of the same title. So, first of all, I'm going to do some introduction. And next, I will go over the problem. And finally, solution, which is up to one loop. And the last section will be so we solved it. Where I will go over why this solution doesn't quite work. So, first of all, let's start part one. The introduction of Weinberg's paper is really nice. He opens that physics thrives on crisis. I think that's interesting. We like physics to be consistent with itself, but really as physicists, we like contradictions. This gives us space to do interesting things. So there are some loose ends to take care of with QFT. And this loose end that I'll be talking about is the cosmological constant problem. So what the problem is commonly stated is that the cosmological constant, lambda, the theoretical value is much larger than the observed value. So what we observe is that if this is us, I have a picture. Let's go here. If this is us, in our Milky Way, we see that galaxies redshift the further away they go. This is saying that the farther away we look, or the farther back in time we look, galaxies are moving faster and faster away from us. So these redshifting galaxies tell us that the universe is expanding all around us. So that's what the cosmological constant is. Or if we define Hubble such that the velocity of a galaxy is proportional to its distance from us, this Hubble constant is the constant of proportionality that tells us the strength of this relationship. And its observed value should give some bound on our theoretical calculation, and we'll see that the bound is much smaller than what we can come up with in QFT. So let's introduce Einstein's equations. If you're not familiar, you can see a standard textbook. So Einstein's equations look like this. So this side is the space, and this side is the stuff. So if you're not familiar, this is my Ricci tensor. This is the metric. This is Ricci scalar. This is my stress energy. And this is the Newton's constant, gravitational constant. Okay. So this equation is telling us that matter tells space how to bend. Matter tells space how to bend. Oh, this should be an arrow. And then the space tells matter how to move. All right. What we can do is that we can add a term to this equation to account for the expansion of the universe. So this is our cosmological constant lambda. Let's just call that Cc. So this is a Lorentz invariant quantity. Let's call this Lorentz variant. This whole thing, I should say, is Lorentz invariant. That says that for any inertial observer, they should measure the same cosmological constant everywhere. Einstein initially introduced this for a static universe solution to his equations. A universe that always existed, will always exist as it was and as it currently is. If we consider lambda greater than 0, we find a solution to Einstein's equations with a static universe with mass density rho, which looks like this. This corresponds to a geometry of a 3-sphere. So this is all points points in 4D equidistant from an origin. And we'll get that with the radius looks like this, and the mass of the universe will look like this. So this was nice because it gives a relationship between the mass density of the universe and its geometry. But what De Sitter showed is that we can have a model with no matter in it, specifically this line element. Sine theta d squared. So this is in coordinates t, r, theta, phi. You get the Hubble is lambda over 3, and the mass density and the pressure is 0. So what this is saying is that we can think of a universe where matter is not needed. And further, historically, in the mid 1920s, I might not pronounce this name correctly, Slipher, he observed redshifts. So redshifts defined as this. And only a very few blue shifts. So he observed redshifts of the galaxies, which is the change in wavelength. Over some let's see. Oh, so he measured this redshift for local galaxies, and only very few had blue shift. If we look at the affine connection for the model above, we get a redshift which goes like Hubble times distance. If we have HR much less than 1, this is saying redshift proportional to distance. What we can also show is that the cosmological constant isn't needed for an expanding universe. If we use this line element, we see that in these coordinates, the universe expands by the scale factor r, big R of t. The galaxies can keep fixed coordinates, but we have this expanding universe. If we look at the expansion, we see that we can have a solution here for an expanding universe with no curvature and also no cosmological constant. So maybe we can drop the cosmological constant. We'll see that this isn't easy because enter quantum field theory. So QFT is telling us that the vacuum has a non-zero expectation value. The fields that permeate everywhere should have some non-zero energy density because of quantum fluctuations. And we can interpret these as particle production in the vacuum. We also know, due to quantum mechanics, that we have this uncertainty relation, we can't have precisely zero energy. So this thing is not allowed. We also make observations of the vacuum fluctuations of the so-called Casimir effect. If you put two plates in close contact, not in contact, close to each other, you could see vacuum fluctuations on the inside will be limited, while on the outside, many more modes are allowed. So there's some minimum mode between the plates, and this causes some force between the plates here, F. So what I'm saying here is that the quantum fields, the quantum fluctuations are real, and we should be worried about them. We should think about their forces, because from experiments we see that they have real effects. If we recall our if we recall the Einstein's equations, and we remember on the right hand side we had this stress energy tensor. Let's say we consider the vacuum and say it has this form. Here we have the vacuum expectation value. Now we rewrite Einstein's equations like this. And rearrange. Just bring the right hand side over. So this we have an effective cosmological constant here, lambda effective. So this is something we can actually measure. We can also say we have an effective vacuum energy. Now, using these, we can try to set some bounds on the vacuum energy, or the vacuum density. We know that the expansion rate today, we say Hubble H naught, is something like 50 to 100 kilometers per second per megaparsec. This is something like half to the 1, 10 to the minus 10 per year. We can get some bounds on the curvature of the universe from this if we set some equation of state for the universe. This is our potential energy of the universe and the kinetic energy. And we say that it's constant. We bring the mass of the universe out here. We have mh squared r squared over 2 minus g over 3 pi r cubed rho over r. And we say this energy of the universe is constant. We can rearrange this and get an equation. 2k r squared, which is, let's put k, define k out here. Or 3 rho. Cool. So with rho 0, we see that we can bound the curvature like so, r squared. And we also can bound the density of the universe, the mass density. So rho critical is defined, we need the density such that the curvature is 0, since we know we have a flat universe. What we can show is because the non-vacuum mass density is not larger than the critical value, we need to have this relationship. We can show that the effective cosmological constant is bound like this, and using this that we've defined above, the vacuum mass density, we can bound the vacuum mass density like this. Now, plugging in some numbers for h naught and g, we find that this is something like 10 to the minus 47 GeV to the fourth. So this is very small. This is like concerningly small, because as you know in QFT, we might get some arbitrarily large value. We think that the expectation of the vacuum could go like mass to the power 4. So plugging in some mass here, we can get something much larger than 10 to the minus 47. Okay, but why should it go like mass to the 4th if we sum some 0-point energies? Well, here, following Weinberg, we do some rough calculation. We can say that the vacuum mass density will sum the normal modes of some field like this. Up to some arbitrary cutoff, 16 pi squared. If we use the Planck scale, where big lambda is 8 pi g minus 1/2, we get an estimate for this vacuum energy, which is 10 to the 71 eV to the 4th. So this is a difference of 118 orders of magnitude. Now we're not happy with that at all. This is a prediction that is totally inconsistent with what we observe. As this density should say that we have a horizon that's somewhat like the distance to the moon, or even less in the case of taking the cutoff at the energy of the Planck mass, as I'll show earlier, as I'll show later. First of all, where does this integral come from? Let's do this calculation a bit nicer. Here I'm referencing this paper. Let's say we have some field, some massive scalar field, and we want to estimate its one loop. This looks like S over X B phi Y F forward. So in this step, we're using the regular Feynman rules, and then from here we use dimensional regularization to do this integral about the K integral, and we get some infinite terms and then some constant terms. And then we'll say this is the vacuum energy, and then we have some volume integral. So we see that this is proportional to m to the power 4. And we have introduced some arbitrary mass scale mu to do dimensional regularization. And we'll want to get some finite number, we're going to have to introduce counter terms to eliminate divergences, where we have this divergence and this divergence here. Wait, is this a divergence? No. Yes. Okay, so we will have that the total vacuum energy, doing this similar routine for all particles, will look like order 1 times the mass of the particle to the 4, to 1 loop order. And now we'll have that this vacuum energy, this vacuum mass density should gravitate. It should have some effect in GR, and we can introduce this effect by changing the measure and introducing the metric. And in terms of Feynman diagrams, this is going to be summing the loops connected to our external graviton fields. Vacuum. So if we consider now just the Hubble horizon, let's make a prediction. Let's take the electron mass and see what the Hubble radius should be. So we know that the Hubble radius will be 1 over Hubble. And we have the Hubble from this vacuum should go like mass of the electron to the fourth. So if we have, let's see, over m Planck squared, we get some Hubble radius 10 to the 6 kilometers. This is the Earth-Moon distance I was talking about earlier. So what I'm showing here is just with electron contributions to the vacuum energy, the Hubble horizon already is close to the moon. This should be very spooky because we don't see the edge of the universe at the moon. So what's going on? Let's go into my solution. Add one loop. So let's recall that we introduce counter terms in QFT all the time. And let's do the same thing and include the counter term explicitly. For x. So here, this is the space contribution to the action. This is the matter contribution. And here, this big lambda is our counter term. So formally, this part is infinite, and we'll have to get rid of the infinity that comes up by introducing a infinity in the counter term. So let's require that we have some renormalized cosmological constant, which is the counter term plus the vacuum energy. And we say that this needs to be less than the measured cosmological constant. So this is just a fine-tuning. Between the finite parts of lambda and the vacuum energy to match with experiments. It's not horrible to do this because we do this all the time in quantum field theory. All we need to do is do it in a consistent way to make some accurate predictions of how the theory goes at different energy scales. So now that we've renormalized the infinities, we go out and measure the cosmological constant, and uh, then we have to fine tune the values to whatever it might be, 118 orders of magnitude. Orders of magnitude. But that's okay because we've already had to renormalize. We've already had to renormalize divergences. Divergences. So renormalizing or fine-tuning by some finite number shouldn't be a problem. So next, we're going to do so we've solved it. So if the cosmological constant problem was that easy, why is it still a problem? Why do people still talk about it? And so, no, the answer is we haven't solved the problem yet. What we have here is an example of a radiative instability. This means at higher loop orders, we need to do further fine-tuning. And this is bad. What we would want is that at higher orders, we don't need to retune our previous orders in perturbation theory in our effective description. So to explain what I mean, let's consider a concrete example. We consider a scalar field phi, and it's has a mass and a coupling, and let's say it's coupled to the graviton. The one loop contribution to vacuum energy, if you do the calculation, looks like this. One loop, m to the 4 over 8 pi squared. So again, we have some divergent terms. We've had to do dimensional regularization and introduce an arbitrary scale mu. So we need to introduce a counter term. Let's call that big lambda, one loop, which looks like this, pi squared. So the renormalized vacuum energy to one loop will look like this. Okay, so now because we have a dependence on some arbitrary mass scale m, what we have to do is go out and measure this lambda. So we can't say just from this calculation alone what the value of the vacuum energy will be because of this arbitrary mass scale. We need to go out and measure and then pick some m so that our calculation agrees with the measurement. This is standard procedure. So we do this all the time. We renormalize the electron charge, and we have to go out and measure it, and then plug in our energy scale so that our calculation agrees with the measurement. But what the issue here is, now we go to 2 loops and we get a diagram that will look like this because of our 5/4 coupling. And we'll get a 2-loop correction that scales like lambda m to the 4th. And this is not suppressed. How did I spell that? Suppressed with respect to our 1-loop calculation. So you should be upset by this. This means that each time we introduce a loop into our problem, we need to retune the finite contribution to the previous loop. So this is the radiative instability. Or we'll say that this theory is not renormalizable. So what this is saying is that we will need the ultimate UV description of the theory. So we've shown our effective field theory description breaks down. So this is the true cosmological constant problem. This is what we should say is the cosmological constant problem. Is that we have to constantly do retuning every time we go further in loop calculations to have our theoretical calculation agree with predictions. It wouldn't be such a problem if we needed to do only one such tuning. And I should mention that there are solutions to this problem that I don't have time to go into today, such as supersymmetry and we have anthropic considerations. We also have changing gravity as a potential solution, and also quantum cosmology. Well, I hope you enjoyed this little talk on the cosmological constant problem. If you have any questions or comments or would like to talk to me about this more, please send me an email. It was super fun reading Weinberg's paper and trying to understand it, and then reading further notes about it. It feels like a sort of black hole you can just get absorbed into, but it's super interesting, and I would love to learn more if you know anything more about it, and I'll be sure to dive into some of these solutions. if I guess in a few months' time you wanted to chat about it or do some reading. Yeah, I hope you enjoyed the talk. I hope you learned something. I hope it was fun. Uh, have a Hope you have a great break and enjoy the summer.